Sorry, wait, I forgot. Okay, that's fine. No problem at all. So actually, the microphone was not unmuted over there. So once again, today we'll talk about some holomorphic structures on Riemann surfaces and their dependence on modular parameters and Lie algebras that can be introduced, Lie algebra structures that can be introduced on the basis of those parameters and structures on the modular space. So holomorphic, or as I said, holomorphic objects depend on modular parameters, and in order to study modular spaces and dependence on complex structures of those parameters, one has to be able to vary those parameters and introduce some invariant objects on both Riemann surfaces and modular spaces. So that problem was partially solved by Rao, but in his representation that those parameters were not fully invariant with respect to changes of coordinates on both Riemann surfaces and modular spaces. Modular space. Actually, his construction was to represent a Riemann surface as the ramified covering of CP1, quite standard procedure, quite standard technique on Riemann surfaces. And he computed variation of holomorphic objects of various types in terms of branch points that can be introduced in Riemann surfaces in order to represent that Riemann surface. So those formulas were quite efficient in various contexts, not closely related, for instance, to Riemann surfaces themselves, but for example, integral systems. So the universal variation formulas, which would be independent in a particular representation of Riemann surface and would be invariant with respect to changes of coordinates, were proved by Alexander Zuevsky in his work. Unfortunately, that work was not. I don't know whether it was published or not, but it's an archive. So let me. Because that doesn't. Okay, thanks. Let me. Well, I did that once before, but I would like to introduce some holomorphic structures and some constructive breaks that would help us to understand how the theory of variation of Riemann surfaces works. That in particular, one of the basic objects that has to be introduced is the so-called prime form, the main reference for that classical science two books of Marmford play. So we consider a Riemann surface of genus G, sigma G, and introduce canonical homology basis A and B of dimension G, and one can. So on the Riemann surface, there exist G holomorphic one forms that can be normalized along integrals over A cycles to deltas, and as written here, and another object which can be introduced at the integral of those holomorphic one forms along B cycles is called a period matrix, which is described to a certain extent the construction of Riemann surface. Let me mention that period matrix is a symmetric positive integer part matrix and defined on the alpha Ziegler half plane, and it has.
Period matrix at the intersection of
the definition is written here. It's just the integral of the biggest of B cycles.
Yeah,
so,
yes, so that's
so
intersection.
Yes. That's the purpose of homology basis.
Because that's only two dimensions.
Yeah. The period matrix that possesses some nice properties with respect to the action of the symplectic group. In further construction, one can use these properties in order to describe invariants that come from the algebraic construction, for example. Sorry, reverse direction. It's useful to introduce so-called normalized differential of the second kind, which has inverse square dependence on the difference of local coordinates, and it can be normalized with respect to A cycles in the standard form. And one can see that the homomorphic forms can be obtained from the second order, the second kind differentials. It's once again integrals from integrals of this differential. So homomorphic forms have relations with those differentials. So once again, let me put here the standard definition of theta functions with characteristics alpha and beta. In this particular case, with real characteristics, it's once again very standard object in the theory of Riemann surfaces, which which allows to express various objects in its form, let's say like this, and it has some nice periodicity properties, including some dependence on the period matrix and shifts of characteristics. And these are quite standard objects. We'll see that many of the other objects can be expressed through theta functions. So one can show that there exist non-singular or characters for a theta function, gamma and delta, so that these conditions are satisfied, so that one is able to introduce the theta functions, theta g function on a Riemann surface, and which can be expressed in terms of derivatives of theta functions in holomorphic one form. So in order to work with not just with integral values of weights of integral values of such forms, one can actually consider half-order differentials of this kind on a double cover of a Riemann surface. So that square root of theta function of this form is a double valued one form on a Riemann surface. Form on the Riemann surface. That object is very useful in order to study systems with odd statistics, like say like that. Well, this is a relation to physics and to mathematical physics and to theoretical physics. This particular object, this half-order differentials can be used in order to describe Fermionic systems for example, vertex algebras. So the prime form is the ratio of theta function depending on some specific integral of holomorphic forms and depending on a period matrix of a Riemann surface divided by two half-order differential, which are given by a beta function of genus G. So the main thing is the main two things which we have to know about prime form is that this behavior with respect to the local coordinates, the difference of local coordinates, and also that prime form is Q-symmetric. So by construction, it's a holomorphic differential form of weight -1/2 on the product of coverings of our Riemann surface, and it has some periodicity. Definitely, it has some periodicity properties along our homology basis, and which are given by some constant, which once again depend on the definition of our prime form. So as I said, the prime form is the main, probably the main object in the analysis on Riemann surfaces, which can be used in order to express various other objects, let's say like that, in various situations. So once again, the main thing is this behavior. So we constructed some object with nice properties, which has this behavior and symmetric, and actually incorporates various data coming from our Riemann surface. So let me mention also that how our differentials of the second kind, for example, can be expressed through prime form in various formulas. One of them is written here but there are many others for other differentials. So it's very useful to computational structure. Yes.
Can you don't so that is the definition of phi and number, or that is the definition of U?
It's a slight difference in notation.
Only for the sign.
It's minus sign, yes, because in certain well, you say that the structure is not totally fixed, so you can play with some coefficients, play around some coefficients for prime forms, and actually this minus sign doesn't bring much difference with for the theory. So in any case, that prime form depends on certain values of characteristics of theta function, and also on actual definition of zeta function. So it's not very important, I would say, like that. The prime form possesses also some transformation properties if we change our local coordinates. So if mu is a function of our local coordinate, and we consider our prime form. So let me first say that we separate differential part and functional part of our prime form to be able to use that k separately from half-order inverse half-order differential. So in certain situations, it's much more. Well, it's enough to use only the functional part of the prime form. So the functional part of the prime form possesses these properties with respect to changes of coordinates, and this formula in particular has plays some important role in further discussions. In addition to so as we saw before, the prime form has this behavior. So it would be natural to think about some object that would have inverse linear behavior with respect to the difference of local coordinates. So that behavior is given by so-called Czech kernel, which also depends on some real characteristic for theta function. And basically, in functional sense, it's an inverse object to the prime form. So see the prime form actually goes downstairs with some decoration of theta function, which are needed in order to keep the definition of the Czech kernel self-consistent. So in the theory, of Riemann surfaces, there is this so-called Birdman kernel, which is related to the prime form, and a Giga kernel is some sort of an alternative to the Birdman kernel, since it has inverse linear dependence on the difference of x and y, and also has some nice properties with respect to modular transformation when the characteristics theta phi are also transformed in some way. We'll see on further slides how it works. So as I said, the Giga kernel has inverse linear dependence on the difference of parameters and a difference of local coordinates, and it's skew symmetric, almost skew symmetric if we also if we take also the inverse elements of characteristic present in the definition of the Giga kernel. It also have some multiplies along the homology basis, and it's actually defined on the once again on the product of two coverings of our Riemann surface, and actually, as I said, it has also some nice modular properties with respect to sp2g on the Riemann surface of genus G, but in this case, in order to show that modular invariance or modular covariance, let's say like that, we have to change also the characteristics of our theta function, and the transformation applies also on period methods according to this formula. So in particular, these properties of Giga kernel are needed in order to prove model invariance for fermionic vertex operator algebra endpoint functions in conformal field theory, and to prove some nice formulas generalizing phase transecant identity of that famous phase identity, which was found by John Fay. So for basically, there are many various and many identities coming from the definition of Giga kernel, and some of them use modular invariance of this object. So let me proceed with, in order to show how it works at lower genus, let me fix the genus equal to 1. So in that case, we have a range at first defined by our lattice standard in the standard formulation. So the prime form in that case is given by the ratio of the theta functions. Very simple object, and we can see it that it depends on specific values of characteristic theta function, and the Giga kernel is given by so-called deformed Weierstrass functions, which are generalization of classical Weierstrass functions, once again depending on characteristics. So those functions were introduced by in our paper with Mason and Tute some years ago, and it can be expressed once again as theta functions, and so here you can clearly see that it's some sort of object inverse to the prime form, and also it can be expressed in terms of key theories with some extra parameters. So this formula is in particular useful for further computations in terms of Q theories, for example, for one-point functions, on Riemann surfaces for vertex operator algebra conforming to theory. So as I said above, it has nice properties with respect to model group, so to Z, so G is equal to 1 in this case, and so that's it. So this is the I decided to give here the definition of those deformed Eisenstein series and Weierstrass functions. This is not very important. This is the Eisenstein series. The notation for the Eisenstein series, which generalized standard definition for classical Weierstrass function and Eisenstein series on surface in elliptic case. So let me now proceed to the main object of the of today's talk. Let us recall a Zuevsky construction concerning an invariant object which form some sort of a Lie algebra on a modular space of Riemann surface. So it's known that quadratic differentials on the Riemann surface are dual with respect to the tangent to the object on the tangent space for a modular space for our Riemann surface. So this is also quite classical description, but let me recall it here. So if we have a point on the Riemann surface, we can consider a small disk D on our Riemann surface sigma G, and let's denote by L the Lie algebra of holomorphic vector fields on the punctured on this punctured disk respect to P. So we have two subalgebras of L consisting of vector fields holomorphic in P and outside P on our Riemann surface. So it's known from Dyer and Tate that the tangent space is isomorphic to the function of L with respect to isomorphic to this quotient. So we can also consider, in addition to M 3G minus 3, which is a modular space for our genus G Riemann surface, another modular space, which is denoted by M 3G minus 3, 1, with one puncture at point U on our Riemann surface. We denote actually the points and local coordinates on our Riemann surface by the same letter, so just to simplify notation. So in that case, the tangent space is isomorphic to the quotient of to this quotient with corresponding Lie algebra, and it consists where the algebra L out U consists of vector fields vanishing at U. One can introduce a non-degenerate pairing between the space L, our Lie algebra, and quadratic differentials holomorphic on the punctured disk in very standard way. And so that if we have n punctures, we can we introduce this modular space 3G minus 3n of n punctures on our Riemann surface, and they once again, as we saw before in the case n1 equals 1, consist of quadratic differentials on holomorphic outside those punctured points on our Riemann surface with poles of order less or equal than 1 at those points. So as I said, this is a quite standard description of the relation between quadratic differentials and algebra L, defined in this way. And in order to introduce our invariance, we have to introduce local coordinates on our modular space M3G minus 3 and corresponding basis for the tangent space, so that we have quadratic differentials G1, G3G minus 3, depending on P, and the main proposition of Alexander Zuevsky in his paper is that the element GP, this quadratic differential, does not depend on choice of coordinates. So that he found a way how to formalize the theory to improve Rao theory of so that it would be invariant with respect to changes of coordinates. So let me also introduce notation for the G prime, which is derivative with respect to corresponding respect to P, and also in what follows, we sometimes omit those dependence on although all objects depend on coordinates on our modular space, we omit this notation in order to simplify the description. So M3G minus 3n is the modular space of Riemann spaces and functions, and these functions are U1, Un, and in that case, we consider the basis for the tangent space is given by derivatives, including dependence on our points on our Riemann surface and points on the modular space. And in that case, the invariant object looks like this. So it includes the previous case where we had no punctures on our Riemann surface, and so it depends only on modular space parameters, and also the object which correspond to this situation of n on point function and function point. It depends on also on some f which include dependence on coordinates on our Riemann surface. So f has a pole for the 1 on the diagonal, and it's holomorphic outside the diagonal. And without loss of generality, one can assume that that it has this form, which reminds us the Giga kernel, which we saw on previous slides. So Alexander Zuevsky also found formulas of transformation with respect to changes of parameters for the object G G hat P, those quadratic differentials in the function f. So by construction, f u should be a quadratic differential with respect to P and a vector field with respect to u. But the actual transformation property is a bit more complicated. So if we once again perform a transformation for P and U, depending on V's, and keep those points non-changed. I mean the points on the modular space. then the modified quadratic differential, which is given by this formula, transforms like a vector field with respect to the whole bunch of coordinates, both on the Riemann surface and the modular space, and as a quadratic differential with respect to p. So in precisely those two formulas are given by a proposition from Zuevsky paper, and you see it has more complicated dependence on the initial differential itself for the transformation of p, which is not a surprise by construction of the G hat. This is the description of the main objects that were introduced by Zuevsky in order to proceed in description of relational on modular space and Riemann surface. Let me switch now to a different object, which actually will be combined in what follows to show some interesting properties of quadratic differentials on defined above. So let me recall the notion of so-called continual Lie algebras, which are due to Saveliev Vershik. This is a generalization of ordinary Lie algebras, and as I said, the notion itself was introduced by Saveliev, and then they together with Vershik, they studied properties and introduced new examples, and actually various examples of continual Lie algebras. The main idea is to replace the space roots for a Lie algebra by some functional dependence on the underlying associative algebra, which we denote here by E. Unfortunately, it coincides once again with notation of the prime form, but it's a different object. So it's associative algebra over RC, and the definition for a continual algebra, for a continual Lie algebra, has four so-called kernels, which are mapped on the product of E to E and or to E, yes, from the square of E to E, and these are some bilinear mappings, and we by means of those bilinear mappings we construct so-called local part of our future continual Lie algebra. Actually, it's quite close to the classical description, and the generators of such continual Lie algebra, actually they depend on elements of E, and I stands for the I stands for the actual space of the local part in our local grading, let's say like this, for initial continual Lie algebra. It's now we apply some restrictions on this. And on these generators, they actually supposed to satisfy commutation relations of this type. So as you see, there we commute various generators for the algebra depending on elements of E, and the result of this computation, they satisfy the same condition as in standard grading situation, and also depend on those bilinear mappings on E. So in order to have a self-consistent description, we have to apply Jacobi identity on those commutation relations, and they result.
Lie bracket.
This is the formal definition of Lie bracket in let's say like this, in principal grading. Principle in the sense of as for ordinary algebra. So we have to the original motivation for introduction of such generalization of Lie algebras was in integrable models. Actually, the purpose was to relate those kernels, which you have on the right hand side, inside generators in commutation relations, with the description of certain integrable system which are not convenient, which were not convenient to describe in terms of ordinary Lie algebras. So that's the idea. So it's so by introduction of those kernels of kernels k 0, 0, k plus minus, and k 0, you can actually enrich the structure of corresponding integrable models. So we will see this in what follow. No. Well, in general, well, what you see, the degree of nonlinearity is quite large, because, for example, you can consider non-commutative E here, and in that case, no. Well, in any case, you can. Well, the main thing here is this this identities which come from the Jacobi identity. So the actual defining identity for a continual algebra are written here for the local part. You see, so everything which satisfies this relation, I mean the set of kernels actually produces a continual Lie algebra. So the main functional thing is hidden here. So to find a solution for those equations, sometimes it's quite a difficult problem, but whatever satisfies this equation actually brings about a continual Lie algebra. Yes. That's yes. In simplest cases, yes, you'll see it further. Yeah. So so the formal definition of first is that a continual algebra is an infinite dimensional algebra, which is given by the ij. I mean so here the role of CR relation is played by this condition actually for Lie algebra. There's the CR relation for classical Lie algebra. So as I said, one can consider non-commutative E, in that case you can find some even more complicated examples of such continual Lie algebra, but it's separate problem. Today we consider only commutative case. So that's one can introduce, depending on which particular grading you would like to get, in which form you would like to. Of course, yeah. But by construction, let's say like that. So for integral models, it's important to keep in mind which sort of grading you consider, so that you can introduce a specific grading operator to represent higher subspaces, let's say like this, of our continual algebra, and which would satisfy the standard grading condition for grading subspaces. And accordingly, you can, in that case, you can get mappings at higher indices, you see, and in many cases, none of them zeros, so that you can get quite complicated structure for a continual algebra depending on an infinite number of, sorry, no, this is the reverse direction, of kernels K and M in both positive and negative directions. So the most general consequence of the Jacobi identity for our generators SK looks like this. So if we want to consider Lie algebra with non-vanishing higher grading subspaces, we actually have to find solution for this equation downstairs for all indices. So it's once again not very easy problem in many cases. And those algebras found their application in integrable systems. Actually, it was shown that many exactly solvable models which didn't find appropriate Lie algebra structure can be actually described in terms of continual algebras due to the functional dependence on the space of roots. So it turned quite useful object for the generalization. In particular, let me mention here two examples. One of them is our contact Lie algebras, given which can be defined by this commutation relations for f hat x and d's with quite standard way. And it turns out that this is the one of examples of contact Lie of continual Lie algebra. So that a contact Lie algebra can be written in terms of our generators, including the kernels standing on the right hand side of commutation relations are given by this formula. See, so the kernels in that case satisfy those equations for those defining equations for kernels of the continual algebra, so that the Lie bracket of this type can be written in terms of those principal grading description of a continual Algebra, which is quite useful in integrable systems. One can see that it's possible to construct an integral model, actually exactly a solvable model in terms of this algebra. So let me shortly remind how it can be done on a two-dimensional manifold. So so we consider the km valued one forms on M in this particular representation, and the constant or curvature condition for A plus in A minus entering this form with respect to Z and Z bar. delta plus and then delta minus corresponds to this derivative. So that when we substitute a plus, a, and minus with the elements depending on generators of our continually in the algebra description of a contact Lie algebra, we obtain some from the constant curvature condition. We obtain some equations on arbitrary functions. So, for example, a plus and a minus can be parameterized by some arbitrary function multiplying generators of a contact Lie algebra and being inserted into the zero curvature, constant zero curvature condition of this type. We obtain some dynamical system. So it's actually precisely written here. So, for example, if we take a plus as our generators, our continual algebra, depending on an arbitrary function, and a minus is the analog of Cartan part of our continual algebra, depending once again on an arbitrary function u, and the minus part in our grading depending on once again g, then we obtain this equation for including elements coming from the description of the contact Lie algebra itself. So this equation can be symmetrized in some sense with respect to the derivatives. So, for example, for that purpose, we take standard transformation, logarithmic transformation of our initial arbitrary function f, and the action of this to on rho, and so that the form of the equation, and using the identity buff, we can write the buff equation in this form. So it's a particular example of a dynamical system which comes from our setup for a continual Lie algebraic setup for a contact Lie algebra. And since it's known from previous experience that the initial contact Lie algebra is of finite growth, which means that the number of generators in our grading subspaces behaves in a good way, let's say like that. Then applying the general theory of Saveliev, which was described in their book in the 80s, then such a dynamical system is exactly solvable. What does it mean exactly solvable? It means that one is able to find explicit solutions for rho in terms of absolutely convergent series in certain domains. So this definition for solvability or integrability is a bit different to two other, let's say, definition of complete integrability, where we find the set of invariants, or to reduction integrability, where we have a collection of reductions leading to integrability of corresponding systems. So in general, the Saveliev theory says that if we have a Lie algebra with some nice properties with respect to growth, and we are able to find such a plus, a minus, in order to write a particular system in terms of constant curvature condition, and we have some enough structure in order to express the solution of corresponding system in terms of some auxiliary object. That means that that theory is exactly solvable. So that the Lie algebraic structure plus the certain conditions on the function that we have to use in order to introduce the system lead to exact solvability. So as we see, the continual algebra description, in particular for the case of contact for this contact Lie algebras, is useful in order to represent the dynamical system in such way so that the Lesnov-Saveliev theory of exact solvability can be applied in the most simple way and brings about result showing the exact solvability of such system. So another example is also quite classical. So Lie Poisson bracket algebra. In that case, kernels k0, k plus minus are given by this, and the commutation relation can be written in standard way for Lie Poisson bracket algebra, and where elements where generators of corresponding grading subspaces can be written in terms of integrals, and once again one can derive certain dynamical systems from this continual algebra description and prove their solvability due to properties of this algebra. So I don't give here explicit descriptions of which kind of dynamical system you can get from this description. It can be found in paper by Saveliev and Vershik, and further in Vershik final Vershik paper describing his progress in for such types of continual Lie algebra. So let me proceed with our main subject of this lecture. Recall those quadratic differentials, GPs, and Adesky found some. He calculated commutation relations of those GPs in terms of some functions that we saw before with the inverse dependence on the local parameter. So it turned out that the commutation relation has this form, and also there is a certain condition which reminds us the Jacobi identity for an algebra of GPs. Similar relation can be obtained both with for G hat, and G is a quadratic differential on the and G hat is the extended quadratic differential, which has also dependence on punctured points. And you see there are nice formulas showing dependence of showing the action of GPs on prime forms, this functional prime part of prime forms, and on integrals of the differentials of the second type, once again expressed in terms of prime forms. So these are very nice formulas for further studies. So let's maybe I skip the examples of particular examples of GPs which are which are different for particular situation of Riemann surfaces, and G the various genesis. So one can also introduce a generalization of GPs as a small GP, which contain also some further dependence on coordinates, on some functional dependence on the coordinates on Riemann surface modular space, and for them there exists also the commutation relation and defining relation, etc. That's similar to Jacobi identity. So all this set was used by us in order to prove that the main proposition, which is as follows. So the elements GP is the generalization for quadratic differentials form a continual Lie algebra G m3g minus 3n, depending on actually in this situation the space of our space E for continual algebra is modular space of Riemann surfaces of genus G with n punctured points. So the description of Zuevsky led us to a formulation of a continual algebra constructed in terms of quadratic differentials in this construction. So it is useful because then we are able to introduce some dynamical systems according to Lesnov and Saveliev in terms of both punctured local coordinates of punctured points on the Riemann surfaces and coordinates on modular space of Riemann surface. So we use the same structure coming from constant curvature condition and specific zero curvature condition from description in terms of generators of a continual Lie algebra of quadratic differentials on both defined on both Riemann surface and modular space, and it's possible to show exact solvability of such system and get rid of condition of even number of coordinates, because so in this case in our construction we have endpoints, so that there's no condition of even number of coordinates as in classical case, for example, for ordinary Lie algebras, in order to be able to prove exact solvability. So let me finish, if I have 1 minute, with, so it's 1 hour or 1 hour and a half? 1 hour. Okay. Just so I just would like to show you in particular case of so-called Ricci flow, which is the example of continual algebra, how the explicit solution for a particular system coming from Ricci flow algebra. It's you see it's the same equation as Ricci flow.
What's on the Riemannian surface?
Yes. Yes. So yeah, I understand your question. So it's just an integral model.
Of any genus.
No, in that case, it's not an example of the how to say, of the continual algebra coming from that modular space description. It's just an example of how to write a solution for Ricci flow.
Question.
Was it on Riemann surface or only on torus?
It's on two-dimensional manifold.
For any, I mean, for any genus, yeah.
Yes,
Because of
yes,
course-
but well, it's a different.
Okay, that's a local.
Yes, it's a local description. Yeah, yeah. So we have this Ricci flow equation. It
Yeah.
can be associated to a continual Lie algebra with a very simple kernels, which is just a derivative with respect to parameter t and one, and the solution, the explicit solution,
Explicit solution.
yeah, can be written in this form in
Right.
terms of generators of
Right,
our
yeah.
continual Lie algebra, some exponentials of arbitrary fields that we have to introduce in order to give a zero curvature description. And also it includes some sort of analog of higher, how to say, highest weight representation for our continual Lie algebra, which can be defined in this functional sense. So the general solution looks like this. General in the sense that any solution of this type can be obtained from the general form, not in the classical sense, the general solution, you see. So in particular for Ricci flow, we can write this solution. So this construction is due to Backus, and for for dynamical system coming from continual algebra description on modular space, this solution are of course more complicated, but the idea is exactly similar. So we can use properties of generators of various grading subspaces for continual Lie algebra to express general solutions for such dynamical system depending on parameters both on Riemann surface and modular space.
So that's the equation on the moduli space of dimension. What is the dimension of the image?
3g minus 3 plus
Yeah.
n.
Okay, so thank you. Now, no more later. Then let's take it.
Thanks a lot.